All right, we'll go from current slide. Okay, we're recording now. Let me go over a couple of issues here. I wish I remembered this while he was in the room. I would have told him. I think I've heard they've opened midterm progress reports, so I will be reporting on that. The two of you are in good shape. He's not, because I don't have a score for him yet, but that's okay. Still can take your research paper at any time, okay? And your second test also at any time. But I have heard that these are not open. Now, I think last time I announced to you about a tax problem solving day that was going to be held in the Millsap building, which is just next door to this one on the outside of the sort of perimeter loop here. Since that was scheduled for March 31st, and as I understand it, nothing's going to be open on March 31st, I assume this is canceled. I don't know that for a fact, but I would assume it is. Okay? So unless you hear otherwise, I would say make that assumption. And I will put down that Peyton showed up today and Keystone is here. Okay. This is actually going to be E for him because he just entered the course. Okay. Amazing. Okay. I won't need it for a bit. Okay. How much have you been following what's going on here? Second? No, I mean about school and stuff.
Oh, I'm sorry. Well, I haven't heard anything.
All right.
This school.
Yeah.
But I know other schools, like high schools, closed down.
Yeah.
Universities, they closed down. I know Just State. I think their last day being open is today and tomorrow, I think.
Yeah.
And that's all I heard.
Okay. You pretty much got it with maybe a few minor differences for us from what Jeff State is. Originally, that's what we were told to. We'd be open today and tomorrow and then teaching online for after that. Now, in my first class, someone said they heard, I don't have the dates in front of me, but through one of them said either April 6th or April 8th, and then in the just previous class of this one, someone said April 2nd or 3rd. So I don't know which one of those dates it is, but then they're going to reassess. Okay. Now, my wife is an infectious disease epidemiologist. She studies these diseases. And she's sort of been tracking, I think, using, I believe it was, what's that clinic? No, the one up in Baltimore or somewhere up there. Real famous clinic. I can't think of the name right now. But lots of people go there for special case treatment and stuff. They have been publishing stuff online. CDC was, but the CDC you can't really trust anymore because they've had a lot of turnover at the top, and they've got a bunch of political people in now, and you just can't believe anything they say anymore, hardly. The scientists there are still good, the ones that are left, but they got rid of a lot of the good scientists too. I mean, they canned them or chased them off or something. So it's hard to say from that, but it's a compound name that I can't think of what it is called. But anyway, she's been following, and of course Italy got started much sooner than we did. But if you put us back on the same timeline, we're following exactly the same trajectory as Italy. Italy, of course, is completely overwhelmed their healthcare system, and they have a pretty good healthcare system. So, to be saying that we'll be back on the 3rd or the 8th of April is really wishful thinking. We're still doing this. We're not even going to be close to the peak by then. The the number of cases are going to keep going up, the number of deaths are going to keep going up. I don't see any way in the world we'll be opening back then. Okay. That said, if we do open back then, and we're still on the curve like this, I'll put it this way. Last night I received a phone call at home from the dean saying, don't come to work tomorrow. Even though everybody else was going to be here because she knows my health condition. She said, you don't need to be there. I said, I've got to go. I've got to get all my books. I don't have any of my materials here at home. They're all at work. I had, grade book and stuff like that, but I didn't have any of my text or anything. She said, oh, yeah, that's right. You will need those. I said, yeah. So that's why I'm here today. I think the rest of the staff will be here tomorrow, but no classes tomorrow. The reason is they're going to use that as a day to get them ready to teach their classes online. And but they didn't want me to come for that, so I'll be working at home tomorrow. Unless I can't figure something out and I have to come in to get an answer. Yeah, but I can't get anyone on the phone. So anyway, I'll, at least for my situation, I can't see that I'll be back before the end of the term. I think it'll still be going like this by the end of the term. So I may be wrong. It may be that we're going to flatten out. And if that happens, thank goodness, fantastic. But the likelihood of that happening is not very great. Okay. And here we have literally perfect attendance today. Okay. Because, remember the third person that was originally in the course that we never saw? He showed up today.
Maybe.
Yeah.
Oh, that's good.
Yeah, but he's been removed from the course, so he's going to have to go take care of all that. So, but he came and got his first 2 tests. So anyway, what I was saying is, as far as I know, I wasn't supposed to be here today because the dean said not in your condition, health and immune system and stuff like that. I said I've got to go in and get all my materials. So since I was here, I had to have my computer worked on, and it took most of the morning. And so I thought, well, let me just stay and wrap up things here. So here's what my plan is. And I would say this is probably going to be for the rest of the term, but they're saying we come back, what, April? Okay, that's 2 nights and 1 second. So one of those 2 days.
I've heard some, I don't know. I was waiting on them to finalize.
Right. The thing is, there has been so much flux since they first came out with something, you just don't know what is there to believe. Last week, Montgomery, head of the 2-year college system, sent out a thing that all out-of-state travel was canceled. You were forbidden to go out of state. And then they added this. If you go out of the state on personal business, you'll have to self-quarantine for 14 days when you get back. Now, this is out of the country. This is out of the state of Alabama. Now, that's for employees. Students could, of course, go out of the state. You could go anywhere you wanted to and come back and bring, if the disease was that prevalent out of state and not in state, you'd be bringing it all back to us, which is ludicrous, of course. But that's what they said. Well, what our plans had been was to go over to Georgia on the farm. I grew up on a farm in Georgia. Both my parents are dead by now. They split the farm into 4, for each of the kids, And so we have a little 2-bedroom bungalow there on our portion of the farm, and we're out in the middle of nowhere. 8 miles from the closest flashing light, 10 miles from the closest red, yellow, green stoplight, out in the boonies, okay? No one, around nobody, okay? And I thought I'd be far better off there than in Birmingham, But if I was going to have to self-quarantine and the school was going to be open, I couldn't do that. Well, since then, of course, that was when Alabama had no cases. That's when Alabama hadn't tested enough people to know if they had had any cases. At the time, they were saying that we had tested the maximum of about 50 people in the state of Alabama. And they didn't even have the results back from those yet. As soon as they started getting results back, whoops, 1, 2, 3, 4, 5, 6. Yeah, I don't know what it's up to now, but it's
Last time I saw it was
12.
12.
Okay.
I think that might have just been Jefferson County.
Yeah, I think so. Yeah, because I thought I had heard of 13 with the majority of those in Jefferson County, but now I think it's even higher. So it's just
But the other places, their hospitals are closed down, so they just don't have people. That's why Jefferson County probably is the only county or one of the few counties in the state that has multiple hospitals.
Yeah. Yeah, the big towns probably do, but all of the rural hospitals pretty much are closed. I mean, if not, they still have very limited ability. I heard on the way in this morning a report from, I think it was somewhere in Kansas. They had a small rural hospital, only had one respirator in the whole hospital. So, they couldn't handle but one case at a time, or one serious case. The rest would have to be sent to something 2 hours away. They were 100 miles from the closest town of any nature, okay, city of any nature. So yeah, we had our heads in the sand or some places unmentionable, but we were just not. We were fooling ourselves to think that it wasn't going to be here. It's here, and it's just going to get worse. And either April 2nd or April 9th or whatever date they set, I was just telling Houston, it's still going to climb.
I know I'm supposed to get treated, but like graduation won't be online.
Have you heard that? Someone asked me.
Yeah. Maybe because I was wondering that we just had our meeting next stuff as we need to get size and everything by the same day, but we're not going to be here by that date, so there's no way everybody's going to come in.
Yeah. A student in my last class was asking me about graduation. I said, I don't have any idea. And also honors and awards day. I said, I don't think they're going to make it. What's that?
I said, from what Dr. Thomas told me, all of this been postponed.
Yeah. I can't imagine that any of it is going to happen because I think we're still going to be climbing at that time. So, and unless this acts more like the flu than it's acted before, because the flu usually decreases in summer, this hasn't shown that tendency because they've been having cases in Australia and it's summertime down there, so, and Brazil, and, in fact, I think I heard maybe even the president of Brazil has it, it's we don't know what it's going to be, but the odds are, I would say summer has a real good chance that it'll be online as well. And then, this is on the other side, and it's not the flu, and so far, only the fact that it's a virus is even similar to some of the symptoms are similar. But back in 1918, when the worst, I think, recorded case of the flu worldwide happened, it was called the Spanish flu, that was very deadly that winter. I think it was 1918, okay? And then that summer it died down, people thought it was over with, the fall came, it was right back again, just came back with a vengeance. And I think even more people died, and it had been so bad the winter before, and it was even worse. So the thing is, even if it does decrease some this summer, it could come back in the fall like crazy. So I wouldn't be surprised. Well, we don't know what its duration is going to be. China has started leveling off, and theirs was definitely an explosion. And theirs started in December. So December, January, February, March. Okay? So 3 months. So if ours started this month, March, April, May, June. So maybe summer. Oh, no, it's not going to be. Maybe fall we'll be able to run in-class classes again. I don't know that. But China has just begun. They opened several of the other towns, but the epicenter, I heard on the news this morning, they were beginning to let people travel and open back up factories and things like that. So it has been amazing. Now, the fact that we've been closing schools and closing universities, closing sporting events, closing things like this, discouraging people from being in big groups. That may, whereas Italy went like this, we may go more like this. Maybe. If so, we're lucky. But still the same number of people are going to get sick more than likely. It's just it's not going to spike as early. And see, the spike is a terrible thing because you don't have enough hospital beds to handle the spike. If you can spread it over several months, then you have a chance of getting some people out, other people in, and getting your protocols down and stuff like that. So on the one hand, the spike, like they had in China, that may be over in 3 months. If it goes this way, it may not be. But on the other hand, we've got lots of hands here, there are some antiviral medications they're coming out with that may be very effective with this. We don't know yet. They haven't been through enough trials, but they hope to have those out by the summer. The vaccine, no way it'll be less than a year. I mean, you just cannot do it. All the testing and they call it efficacy, how efficient it is, and safety. They have to do all those things before they can release it. And you just can't do it. I mean, they start working on the flu vaccine for next year hardly before this year is over with. And they have to guess what strains will be coming through next year. What they do, they look at southern hemisphere and see what strains seem to be happening down there, getting started, and then they try to do the vaccine so they can handle them here. But sometimes they're wrong. Sometimes they don't hit them right. But we'll see what happens. But anyway, what the bottom line is, I'm not supposed to be back on campus anymore until further notice. I don't know when that further notice will be. So let's just figure we're going to be doing till the end of the term online. And here's what I'm hoping to do. My wife has used Zoom before. Have either of you? Okay. It's a package, and one of my students had it on his laptop, and that's the other reason I was late getting this side started, because he was showing me how he uses it. He uses it for work and meetings with clients or whatever, And it looks pretty easy. And what you do, you get a code. I'll be hosting it, so I'll get the code. And with that code, then I'll email that to you like 5 minutes before the classes start. Because there is a time limit on the free version. My wife heard 40 minutes. That's what I've been hearing, but this student said he's used it for up to an hour and it hasn't cut him off. Now, if there's high usage, it may cut you off at 40 minutes. That's the minimum. But if they're not crowded, they'll just let you keep running. So what we'll do is I'll send that this class starts at 2:30, right? Yeah, 2:30. Then about 2:25, I'll send out the code. And if you're not there right then, it'll still be there on Blackboard. Okay, it'll be an announcement and an email. And I'll get started then at 2:30 and go as long as it'll let me go. And then if it shuts me down, I have to get a new code, and then I'll send out the new code, and then we'll finish up the class. And when you log on, and you'll need to get Zoom on your phone or computer, either one, and then when you log on, I'll see your picture pop up, or something will pop up, that indicates you're there, and that way I'll do attendance, because I still have to take attendance. And then I'll try to use, if I can, use Screencast-O-Matic and teach just like I've been teaching before. PowerPoint, we don't have PowerPoint in this class, but we'll try to do it just like we've done before. All you'll see is my screen. You won't see me. But I can still ask questions. You can hear me. Now, I think only one can respond at a time, but you don't have to be, whoever starts talking first, but maybe not, maybe more than one. I've never used it, so I don't know. So that's what we're going to try to do. Does that sound reasonable? I hope by Wednesday I'll be okay on it. I'm going to try to get started tomorrow and do my 4 classes tomorrow on it, if I can. And if I can't, then I'll work something out. But hopefully by Wednesday I'll have it down. and we'll try to do that. And that's how we'll do from now on. When you finish the test, scan the test and send it to me PDF. If when we come time for the next test, I will scan it and put it on Blackboard, attach it to an email on Blackboard probably. Okay. And how does that sound? Then when you finish that one, you send that back. And your research papers, when you finish those, scan them and send them to me. Now, if you want to send them to me Word, that's fine. I can take them that way. That's perfectly fine with me. And if I happen to type your test or stuff like that in Word, I may send it to you that way. But my wife said it's actually better to do PDF because then it's harder to change a PDF file than it is a Word file. Anyone with Word is going to change the file, you know. And not that you would do that. Why would you want to? You probably make the problem harder. But so I'll try to probably do whatever. Most of the tests I make out in WordPerfect, so I've got to do a PDF anyway because no one else uses WordPerfect. But that's one reason I do it. Number one is the equation editor is so much better than Word. And number two, that even if someone gets my file, if they don't have WordPerfect, they can't do it. That's what I had to get loaded on my laptop because I have it on my desktop. I didn't have it on my laptop. And it took her all morning and she couldn't get it done. And then early afternoon she got it done. Okay. Any questions on any of that? So that's what we'll try to do. Where we are now is chapter 4, higher order differential equations. And we're in section 4.1.1, which is initial value and boundary value problems. We have done the initial value part and we've done example 1 and 2. Now we're getting ready to get into the boundary value. Okay. The theorem that we base this on is existence of a unique solution, and this was for initial value problems, not boundary value. We're going to get to that in a minute. But the requirements in this is in 4.1.1, the theorem 4.1.1, that all of your coefficient functions, the a sub x's, okay, let me get my pen set up. Okay. All of your a sub I of x's, these are the coefficient functions of the various derivatives that you have here, that these be continuous. Okay? They be continuous. Okay? And of course, the first one, a sub n of x, cannot be 0. Because if it were 0, it wouldn't be an nth order polynomial. Nth order differential equation. Okay, so a sub n of x cannot be 0. For every x in the interval that you're dealing with. Specifically, if a sub n of x is equal for even one x in that interval, then the solution of the linear initial value problem may not be unique, or it may not even exist. So that uniqueness theorem that we had to have them being continuous and not a sub n not equal to 0 for every x in the interval. Okay. So here's a function they gave. I think I'll clear that because I don't need it, but I may need the room. Man, it's been a rough day and my head is hurting like crazy. I don't know why it just started. Y is equal to cx squared plus x plus 3. Now, just looking at that, I would say this could be a solution for a first order differential equation because it only has one variable in it. Okay? It says it is a solution of this initial value problem. But look at this. This has 2. This is second order. X squared y double prime minus 2xy prime plus 2y is equal to 6. where y of 0 is equal to 3, and y prime of 0 is equal to 1. Now this to me is even more problematic. If this didn't have initial conditions in it, I would expect two constants, okay? But with the initial conditions, you should have lost both of your constants. You shouldn't have a constant in it. So this is even more problematic, okay? But it says, verify that this is a solution for this differential equation, initial value problem. So let's do it. What would we need to do first? Y prime. And what would that equal? 2cx plus 1. And then y double prime would equal 2c. Okay? So let's plug into what we have here. That would be y double prime is 2c. That would be 2cx squared minus, I'll write it this way, 2x times 2cx plus 1 plus 2 times cx squared plus x plus 3, and supposedly that's equal to 6. All right, let's see indeed if that's true. 2cx squared minus 4cx squared minus 2x plus 2cx squared plus 2x plus 6 equals 0. Well, here, if you can read through my ugly writing here, is a minus 4cx squared and 2cx squared and 2cx squared. That adds to plus 4, minus 4, that goes to 0. Minus 2x plus 2x, that goes to 0. Oops, 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 oops. You let me get away with it. It wasn't equal to 0, it's equal to 6. And 6 is equal to 6, sure enough it's true. And that should be for any value c. Wait a minute, okay? Oh, we didn't try this. Let's see if this also works. When y is equal to 0, when x is equal to 0, y is equal to 3. That checks. And when x is equal to 0, y prime is equal to 1. That checks. Okay? From here and there. So everything fits, and yet we still have a parameter we can't account for. The c. And I would have thought all your parameters would have disappeared. Okay? This is true for any parameter c. In other words, there is no unique problem solution for the problem. Okay? Well, what's wrong with this picture? The theorem says there should be a unique solution. Here we have an infinite number of solutions. For any value c, this will work. Well, let's see if indeed that's true. Oh, this is supposed to be all real numbers x. Well, x equals 0 is a real number, and that's your coefficient. So no, this wouldn't be true. This would only be true for x is greater than 0 or less than 0, but it cannot be true for x equals 0. And at x equals 0, you have 2y is equal to 6, so y would have to be equal to 3. So in other words, this is saying this is good at x equals 0 only if y is equal to a constant value of 3. That's not a very liberal problem. No. Because you had something in your domain that gave you an a sub n equals 0, that threw everything out. So So this would only be true for positive x's or positive x's or negative x's would not be true for x equals 0. It couldn't be true for that. So I don't know if that's what they were. Yeah, that is what they were getting at. So now let's move to boundary value problems. Now these are problems that do occur in real life, in physics, in engineering, in all sorts of areas. Another type of problem consists of solving a linear differential equation of order 2 or greater in which the dependent variable y or its derivatives are specified at different points. Just erase it, I wish I hadn't now. Remember, both of those conditions were at x equals 0. That's an initial value problem. And now the initial value doesn't have to be 0, but it has to be the same for every condition. In a boundary value problem, you may have one condition here and another condition here, and still have a legitimate problem. Okay? And you can almost picture this. Do any of you play guitar? You know what it's like to play a guitar? You hit a fret, and you set vibrations in a string. You're fixed here, and you're fixed here. Okay? And that gives you a certain note. Okay? Because that's a boundary value problem. If you had this string without any fix to it, you don't have any notes. Okay? So those are boundary. That's a dumb example, but it is a boundary value problem. So here would be such an example. A sub 2 of x times d2y dx squared plus a1 of x dy dx plus a0 of x times y is equal to some g of x. Now that looks just like our linear differential equation, linear differential equation of second order differential equation. Nothing's changed what we have been doing. Here's where the change is. Subject to y of a is equal to y0 and y at b is equal to y1. What makes this different from our initial value problem, actually two things make this one different. An initial value problem, both of these values have to be the same. And also with an initial value problem, since both of those are the same, you couldn't have the same thing giving you two different values. That would be a function. Okay? But this would be first the function, that would be the first derivative. Well, you can still do the first derivative of a different point here and have a boundary value problem. Okay? And those are often called BVDs. VVP. I think VVP was a type of underwear, so I don't know. Anyway, VVP, boundary value problem. And these are called your boundary conditions. Like initial conditions, these are your boundary conditions. Okay. And a solution of the foregoing problem is a function satisfying that initial differential equation on some interval I that has to contain both A and B, okay, whose graph passes through the 2 points AY0 from here and BY1 from there. Okay. Now, this was a second order differential equation. Other boundary values could have been this. Y prime at A could be your Y0, while Y of B could be your Y1. That would be okay. Or Y at A could be Y0, while Y prime of B could be Y1. Or Y prime at A could be Y0 and Y prime of B could be Y1. Okay? So you can have both of these functional values identified, one functional value, one derivative, or one derivative, one functional value, or two derivatives. Any one of these four possibilities could be your boundary value problem. Okay? Setting your boundary conditions. Okay? But you only need two for a second order differential equation. Okay? Y1 and Y0, excuse me. Y0 and Y1 are arbitrary constants. Okay? And those three pairs of conditions are just special cases of the general boundary value condition, boundary conditions that would be this. These are a bit bizarre. Alpha 1 times y at A plus beta 1 at y prime of A is equal to some gamma 1. Now this is enough Greek letters for you. Alpha 2 at y of B plus beta 2 y prime of B is equal to gamma 2. Okay? Now, no, I got those backwards. No, I did them right. Yeah. Okay. I was looking at the wrong set. Now, here's yet another problem with boundary value problems. Just because you have differential equation, linear differential equation with boundary values identified, they don't guarantee you a unique solution. Okay? Initial value problem, if your A's are all continuous functions and your A sub n is not equal to 0 at any value in the interval, you have a unique solution. You can have the same things here, A's being continuous functions, A2, A1, and A0 continuous functions, and the A sub 2 can not equal to 0 for any value x in the domain in the interval. Okay? You still may not have a unique solution. So here's example 3, which illustrates that. This goes back to example 9 and 1.1. They like to conserve their examples, okay? It says they solve a two-parameter family of solutions of the differential equation x double prime plus 16x is equal to 0. Okay? And here's what their solution was. X is equal to C1 cosine 4t plus C2 sine 4t equal 0. Wait a minute. I got it in the wrong place. That's you don't have a 1 equal sign. I was looking at the equal sign from before that. I said, that can't be right. Okay. Yeah. Now, you could go back and verify this again. We did it earlier. But you know what's going to happen. The first derivative here will be a minus 4 C1 sine 4t plus 4 C2 cosine 4t. That's the first derivative. The second derivative would be a minus 16 C1 cosine 4t minus 16 C2 sine 4t. And there is a 16 up there. Now here it looks like it. this would then give you, you factor out the minus 16, you have minus 16 times this original x is equal to, you know, plus, so, 16 times this thing, minus 6, yeah, and this is a minus 16 times that thing, that does add to 0. So that is a solution for that second order differential equation. Okay? Now, it says, suppose we now wish to determine the solution of the equation that further satisfies the boundary conditions that x of 0 is equal to 0 and that x at pi halves is also equal to 0. Okay? Two boundary conditions at different points for t. One t is 0 and one t is pi halves, but, and they just happen to have the same value, that's okay. So if that now combination here is your differential equation, what happens when you plug in the values here? This would be x is equal to c1, and the cosine of 0 is what? It's what? 1, okay? So that would be c1 plus sine of 0 is 0. So this would then be 0 is equal to c1. Because your x value is 0 when the t value is 0. You plug in the other one, and you have, this is also going to be the 0 on the outside, is equal to c1 times the cosine of pi half, oh no, 4 times pi halves. That would be 2 pi, right? You plug up pi halves in here for t. What's cosine of 2 pi? 1. Okay? So you have c1, and you plug in the pi halves there, and you get 2 pi. Sine of 2 pi is 0. So again, you get c1 is equal to 0. You have absolutely no value for c2. None. Okay? All you know is that both at 0 and at pi halves, you have nodes there, zeros. Okay? And you have no control, no indication of what c2 could be. Okay? Oh, this was on the wrong page. It has infinitely many solutions. And the reason for that, C1 was 0 in both cases here. So what you have is x is equal to C2 sine 4t for any value of t in the world. Oh, I'm sorry. Any value of t, but also any value for c. You don't have a unique solution. Arbitrary coefficient. Constant C2. Okay. Now, if you had changed the boundary value condition in this one, the second one, to be this, x of pi 8 is equal to 0. Okay? Now what would you have? This boundary condition is still the same, so you get C1 is equal to 0. But when you plug in this on the second one, you have 0, that's your x, is equal to C1 times the cosine 4 times pi eighths is pi halves. What is cosine of pi halves? 0. Okay, so you don't have anything there. Plus C2, and the sine of pi halves is 1. So then you have C2 is equal to 0. Up here it gave you C1 of 0. Here you get C2 of 0. Well, guess what, folks? What's your solution? Your solution is x is equal to 0 plus 0. Okay? Yeah, forget that. That was the earlier thing. Then you have no solutions. I mean, that's not a very meaningful solution. It's basically your trivial solution is the only solution you have. Well, it produces a trivial solution. Hence, x equals 0 is the solution of the new boundary value problem, and we'll find out later it is indeed the only solution for that. And that's just not a very satisfying solution. X equals 0, yeah, that works. All right, well, let's try a third thing to it. Everything else is the same, only this time they'll say x of pi halves is equal to 1. Okay. Now we still have that 0 is equal to C1. That's still fixed because the first boundary value didn't change. But the second boundary value would be this. 1 is equal to 4 times pi halves is what? 2 pi. And cosine of 2 pi is 1. So you would have 1 is equal to C1 oh, but C1 is 0. We already know C1 is 0. Okay, forget about that. 1 is equal to, well, sine of 4 times pi halves is 2 pi. Well, sine of 2 pi is still 0. So it looks like C2 is now, yeah, you have no solution at all. In the first case, you had an infinite number of solutions. The second case, one and only one solution. And the third case, no solutions at all. Because you can't have both of those being true. That C1 yeah, I believe that comes out to be a situation where you have absolutely no solution. So, boundary value problems you have to watch out for. Okay? Sometimes they work out very nicely, other times they don't. Okay? This is the one for the part A that we did. And sure enough, you have an infinite number of solutions. Your function could go like that, like this, like this, like this. Anything that goes through this point and that point at the same time, that would work. And they don't even have a model. You could do a single half wavelength or full wavelength. You could do just about anything as long as you meet those two conditions. The others either only have one solution or absolutely no solutions at all. All right, that ends 4.1.1. Let's move on from there. I'm so sorry. Today has just been a crazy day all day long, and I had no time to finish eating my lunch, so that was one thing. Plus, this being severely anemic by this time in the afternoon, I'm just almost worthless. I just don't have any energy left, so I apologize for the yawning. It's not that I'm bored, it's just I have no energy. Okay, 4.1.2 is talking about homogeneous or homogeneous, okay, I left off an E here, equations. Okay, now, earlier, 2.5 on page 72, you have one definition for homogeneous or homogeneous equations, and that's if the two differential forms, if your function is x cubed plus y cubed. There's something that they both have the same degree. Okay, we talked about those before. This is a different meaning for homogeneous or homogeneous equations. Here's what we mean by these homogeneous equations. Here we have our good old nth order differential equation. And know how it goes. A sub n of x times d, the nth derivative of y with respect to x to the nth time, plus a sub n minus 1 of x times d n minus 2 dx to the n minus 2 plus a sub n minus 3. I'm sorry. My screen is wobbling on me, so it's hard to write. N minus 2 of x is equal to d, I'm sorry, not is equal to, times d sub d, the n minus, goodness gracious, I got off in my thinking here. I got ahead of myself. This one's the n minus first term. This is the n minus second term. Dx to the n minus 2. Okay? Plus dot 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 all the way down to plus a sub 3 of x d triple prime, oh that's just right, d3 y dx cubed, and they've been putting the y's in there. I left them off, these two. Okay. Plus a sub 2 as a function of x, the second derivative of y with respect to x squared, plus a sub 1 of x dy dx, plus a sub 0 as a function of x, y is equal to 0. That's what we mean by a homogeneous or homogeneous equation in this context. Okay? That the linear nth order differential equation is equal to 0, as opposed to being some g of x. It's equal to 0, not equal to a function of x. Okay? So if you had a g of x here on the right-hand side, instead of the 0, this would be a non-homogeneous or non-linear homogeneous. Equation. Okay? If you have the g of x, it's not homogeneous. If you have a 0 at the end, it's homogeneous or homogeneous. Okay? Now, when we have one with the g of x in it, the first thing we're going to do is change the g of x to 0 and solve the homogeneous type. Then we'll go back and solve it for the g of x. That's going to be our procedure. So, even if you have one with a g of x, the first step is to make it homogeneous. And then solve that way, and then go back and append your solution with the g of x. Okay? Now, here are your two assumptions for all these. They don't sound very new at all. All of these a of x's, every one of these a of x's has to be continuous, just like we had before. Okay? And, of course, like before, a sub n of x is not equal to 0, just like we had earlier. Okay? Same conditions apply. Now, this leads to, and they say in calculus, differentiation is often denoted by these capital letters D. It is sometimes, but don't get too carried away by it. Most of the time, we still use dy dx, d2y dx squared, and all that kind of stuff. But they're now making the operator capital D, and that operator capital D with a y after it means dy dx. So in other words, the operator D is equivalent to, I don't know, I'll put 3 lines there, d by dx. Okay? That's what it's equating. You put a y after it, put a y after both of them. dy is dy dx. Okay? Now, with that in mind, d 2y would be d by dx of d by dx of y. Okay? Which is another way of saying d2y dx squared. Okay? That's what we mean by d2. And you can get this almost by thinking you square this, and this. And that's exactly what you got here. d2y dx squared of y. That is exactly what you've got. And you can keep on going as high order as you want to do it. Okay? So then what basically you turn into is making your operator look like a polynomial in y. Okay? Well, not in y, but multiplied by y. And then a lot of things you do with polynomials, they work here too. Amazingly, they do. Okay? So that's one reason they go to that, is it sort of leads you down the primrose path to exactly where they're wanting to take you. All right. So, along that line, then let's think of something like this. Polynomial expressions involving d, they could be something like d plus 3. If d plus 3 of y, that would be dy dx plus 3y. Or dy dx plus 3y. Okay? That would be what that was. This one, play around all you want to with it, d2 plus 3d minus 4. If that's your operator on y, that would be second derivative of y with respect to x plus 3 times the derivative of y with respect to x minus 4y. That's all it means. But you write these as if they're polynomial operators. They're operators, and these are operators, not variables, but you treat them almost as if they were things. Guess what you can do with it? Listen, yeah, you can. Make this, factor this as d plus 4 times d minus 1. And then, that would be, and it's amazing what you can do from just using your little operators now. They get more complicated too. 5x cubed d3 minus 6x squared d2 plus 4xd plus 9. Okay? That's definitely a polynomial operator. The difference here is these are, when you have something other than a d, it's all three of those are integers. Okay? Okay, and that's all you have. Down here, the things you have other than d actually have functions of x's in them. Okay. Now, I don't know for sure, but I think it's just happenstance that these are always the same powers here. They don't have to be. Okay. As far as I know, they do not have to be for them to be operators. Okay. So I don't know why they chose that one to illustrate and made it seem like they have to be the same, but they don't. Okay. So in general, they define an nth order differential operator or a polynomial operator. Now, this is where it gets almost squirrely to me. They come up with a new operator, and this is a L, which is a linear operator, which is a sub n of x times d superscript n plus a sub n minus 1 of x times d to the n minus 1, the n minus first derivative, plus dot, 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 goes all the way down. I would have put more, but I'm running out of room. A sub 1 of x d plus a sub 0 of x. Okay, that would be your linear operator. It's linear in these operations. These are all polynomial powers of d, which itself is an operator. Your coefficients are just happen to be functions of x. And there's nothing here that says these powers of x here have anything to do with the number of derivatives, like they made it seem here. You don't, okay? There's really no reason to put that. Well, there may be some problems that you would have, okay? And these are linear operators. I'm going to give you a couple of rules for linear operators. I wish I still had room on this slide. I'm running out of room rapidly, so let me go and erase all the slide and start over here. Here's a couple of features of any linear operator, including your differential operators. If you're taking the derivative of a scalar c times a function f, you can pull the c to the outside and do just a d of f. Okay. That's one. And the other is if you're operating with a d on a sum or difference of two functions, f of x plus or minus g of x. Now, the book only does the positive, but it's still true for negative. This would be the same as D operating on f of x plus or minus D operating on g of x. Okay? So basically, what we say is the scalar multiple rule holds and the sum or difference rule holds. Sum or difference rule holds. Okay? And those are just two more indicators these are indeed linear operators, because they both fill there. The differential operator L possesses a linearity property, just like this. That is, L operating on a linear combination of two differentiable functions is the same as the linear combination of L operating on the individual functions. All right. And they form a conclusion from this by combining both of those together with your L operator to say this. L operating on an alpha of x, and it's plus or minus, but I'll do it like the book and just put plus beta g of x okay, is equal to alpha times L of f of x plus beta L of g of x. Okay. Now, I think I've got everything covered in here. Okay. Now, I don't know if you're used to seeing things like this. If and when you take linear algebra, I know Houston has, I think both of you have that. We were getting toward this in the linear algebra course. You see, this is and this is like your constant multiple, okay? But your sum or your differences here make your sum and difference here. So this one linear operator you can pull out the constant and make the linear operator on that, pull out the constant here and make the linear operator on that. So in other words, distribute the linear operator inside the braces and then pull the constants outside the braces, and you have the same height of the deal. Okay. Equal sign at the end. You don't need anything else out there. Okay. Yeah. Okay. How are we doing time-wise? Over. Uh-oh. Extra charge. No, I'm just kidding. Okay. Next time, which hopefully will be online on Wednesday, we'll start with differential equations, which I thought that's what the whole course was about. But this is the one on page 122. And let me erase the line down here so I don't get it confused with that place. Okay, homework exercises here. We made decent progress, but still this is the first section of every one of these chapters just goes on and on and on and on. Okay? So in 4.1.1, which we had already done most of until today, we finished it up today, either 1 or 3, if those answers are in the book, back of the book, 5 or 7 if those are in the back, 9 if it's in the back, 11 if it's in the back, and 13 if it's in the back. Now with 4.1.2, me just make sure. Actually, we haven't done an example of that. So you don't have to worry with any of those yet. We'll hit those next time, and then we'll add a bunch of those. And then we'll hit the non-homogeneous or homogeneous equations, and we'll show further how to go there. Okay. Now, frankly, it's all sort of talked about from top of your head type concept in 4.1. When we get over to 4.2, that's a very short section, but 4.3 is when we hit the real meat. It seems like it's always the second, third section before you really start doing some practical examples. The first couple of sections just are covering esoteric stuff, which is sort of important, but it's out there. But you don't really get to specific stuff until point 2 or 3 or 4, maybe even sometime. The last chapter, I know 2.1 was just this general stuff. Finally, 2.2, I think, was separable equations. Then we started doing specific kinds. Same thing here. Hopefully, we can get through 4.1. 0.2 next time and into 4.1.3, maybe even finish that. When we get that done, then again, reduction of order is another sort of general, but it's a very short general section. And then we'll finally start doing specific linear equations with constant coefficients. And that is going to be the real place where I feel like we start doing differential equations rather than just talking about differential equations. So anyway, we'll pick up and go. I'll try to have Zoom by next time, and that will be Wednesday. Wherever you happen to be, pull out your computer, your phone, get on about 2:30, 2:25, 2:30, something like that. And hopefully you'll find a code there. You can log on. Now, I don't know if you have to have Zoom loaded ahead of time or not. Probably not a bad idea to. I haven't done it yet, so I don't know. I've just been shown by a couple of students and they already had it loaded, so I don't know how automatic it is. They made it seem like it wasn't bad. And you want, I would guess you want the free version. And like the student last time said, he's never been stopped at 40 minutes. He usually has gone an hour or longer and still running fine. I think that if they have a lot of volume, they do end you at 40 minutes, and then you have to start over again. So we'll see. Hopefully we can maybe do the whole class in one sitting. But if not, we'll stop, load again, and we'll reload and go. Okay? I don't want to put that in there. I will put these. Any questions? Yes? Oh, yeah, sure. Let me get a copy. This is the second test, number 5, right? Oops, that's still test 1. Here's test 2, number 5. Okay? Yeah. That's the way to go.
But, when I went to doing it, I would get my partial derivatives for each function, and it'd be the same exact terms, but the the signs would be wrong. And so I was playing around with it the other day, and I just kind of changed the signs of the initial equation just to see what would happen. And I was just wondering, Could it be that the signs are wrong?
Let me take a look and see if I can find my test bank. I have it in here. I have that in here. Just take a look. Yeah, everything's right. I think I typed it right. I haven't shut this down yet, so let's take a look. Okay, I'm going to clear the screen here. Okay, let's see. Your m of xy, this is what you talked about, right? That's equal to y times log x minus log y. Your n of, okay, wait. I think I see. Okay. I think you may be doing it more right than you think you are. Okay. Okay. This is your standard form. Notice that this. So if you change the sign and put a there and set that equal 0, then you can set it.
Yeah, I did that.
Oh, you did?
Yeah, like, you take it to the other side, it's going to be negative, and then I'll sign this one first.
Right.
And when I did that, I was scared to get the wrong sign. I had the right terms, but the wrong sign.
Okay. Let's see now. Remember, I can't remember if this is one. Even if it's not exact, you can make it exact sometime. And that's the, but I don't think that's the case here, but let's just see, okay? Where did I have it? Here it is. Okay. So to make it easier, it doesn't really matter which way you go. Well, let's just do it this way. To change the signs, I'm going to change sort of the order too. X log y plus y minus x log x, right? That would be your n of xy. Right? Okay, I swapped it over, I brought it to the other side so you have equals to 0. Okay, I've left off the dx and the dy. Yeah, I'll put them in. Dx here, and then this will be a plus, and this will be your dy here. Okay. What's that? Wow, it doesn't show up on my screen. What in the world is that? I've never seen that. See, I don't have it on my screen, so I can't hit anything. See, my screen is completely blank. What's that? Oh, okay. I don't know what it meant. I don't know what it did. Now, maybe I got too far from the computer and the audio went out. That may have been it. Okay, so you do the partial of this side with respect to y. Okay, let me make sure I did. Yeah, okay. All right, I'll just put this here. Okay, and you'll do the partial of this one with respect to x. Okay, let's see what we get. That's a product rule, at least to begin with, the roughest thing. And so it'll be the first y times derivative of the partial of this thing with respect to x, which the first term won't contribute anything, but that will be, with respect to y, minus 1 over y. So I think that comes out to a minus 1, but we'll come back to that, okay? Plus the derivative of this, which is 1 times log x minus log y. Okay, so this is log x minus log y minus 1 on that side. Is that what you got? Okay. Well, let's do the same thing here, only this with respect to x. So the first term here is going to be a just log y, right? And this one's going to be a plus nothing, okay? And the next is going to be a product rule, so that's going to be a minus x over x okay, minus log x, I think. Okay, I see what you mean. You get a positive log y minus 1 minus log x. Okay, and they aren't quite the same. Okay, one sign in each is a little different.
So you think, is it the one who make it exact, or do you think it's
Yeah, I think it's the one you have to then do another step and make it exact. And that you get from the these things you just did. I didn't write them down here. On the wrong page. Yeah. Your integrating factor will then be your, and you can try either one of them on page 69. Mu of x is the e to the, I write the print so small, it's hard for me to read. Integral of, this is our m, this is our m sub y. Well, this one's the m sub y, and this is our n sub x. Okay? So it's either the integral of m sub y minus n sub x over n. Okay? This one minus this one over this one. Okay? Or it's the integral e to the integral of n sub x minus m sub y over m. So you just have to try each of those and see which one comes out better. So they're so close, it looks like they would be, it would work, but they don't quite work. Okay? And So yeah, I think that's the way to go with that. Yeah. I couldn't remember, it's been so long since I'd worked it which way I did it, but it was, yeah. You have to pick it up and rub your hands on it. All right, well, in case I don't see y'all again, good luck. I'll be seeing you on virtually, but I may not see you in person again because I'm not even sure we're having graduation or any of that kind of mess. We'll see. All right, but good deal. I hope to see you Wednesday.